Welcome back. We are glad you are here. Welcome to Rayat Shikshan Samstha's ROSE project, Wave Optics lecture number 5 and presented by Swati Mahadik. Optical path. What is meant by optical path? The path that a light ray follows as it passes through an optical medium or system is often called the optical path. It represents the distance light travels in vacuum in the same time it travels a distance d in a medium. Optical path. The phase of light wave having angular frequency omega and wave vector k traveling in a vacuum along x direction is given by kx minus omega t. Remember that we have that wave vector k and angular frequency omega are related as k is equal to omega by v. V being the speed of the wave, which is c in vacuum. If the light wave travels a distance delta x, its phase changes by delta phi is equal to k delta x is equal to omega delta x divided by v. If the wave is traveling in a vacuum, k is equal to omega by c and delta phi is equal to omega delta x upon c. In case the wave is traveling in medium having a refractive index n, then its wave vector k dash and angular frequency are related by k dash is equal to omega by v is equal to omega by c by n into v. V being the speed of the wave in this medium. Thus, if the wave travels a distance delta x in this medium, the phase difference generated will be delta phi dash is equal to k dash delta x is equal to omega n delta x by c is equal to omega delta x dash upon c. This is equation number 7.24 in our textbook, where delta x dash is equal to n delta x. This is the equation for optical path. Thus, when a wave travels a distance delta x through a medium having refractive index n, its phase changes by the same amount as it would if the wave had traveled a distance and n delta x in vacuum. We can say that a path length of delta x in a medium of refractive index n is equivalent to path length of n delta x in vacuum. N delta x is called the optical path traveled by a wave. Thus, optical path through a medium is the effective path traveled by light in vacuum to generate the same phase difference. In vacuum, the optical path is equal to actual path traveled by n is equal to 1. Optical path. Optical path in a medium can also be defined as the corresponding path in vacuum that the light travels in the same time as it takes in the given medium. Now, time is equal to distance upon speed. Therefore, time is equal to distance in medium upon velocity in a medium is equal to distance in vacuum divided by velocity in vacuum. Therefore, optical path d vacuum, it means the distance in vacuum is equal to velocity in vacuum upon velocity in medium into distance in medium is equal to n into d medium. Thus, a distance d traveled in a medium of refractive index n introduces a path difference nd minus d is equal to d. It simplifies d into n minus 1 over a ray traveling equal distance through vacuum. The path that a light ray follows as it passes through an optical medium or a system is often called the optical path. What is meant by optical path? All these equations for optical path. Light ray ने म्हणजे एखाद्या कोणत्याही मीडियम मधून म्हणजे जे काय एखादा इन्स्ट्रुमेंट असेल आणि त्याच्यामधून जो लाईट ट्रॅव्हल होतोय मीडियम मधून किंवा व्हॅक्यूम मधून, तर त्याला म्हणतात त्या लाईटचा जो पाथ आहे त्याला म्हणायचं ऑप्टिकल पाथ. And all these equations for optical path. Now, phase difference. फेज डिफरन्स वेव आली की त्याच्यामध्ये ऑप्टिकल पाथ आला की फेज डिफरन्स आला, ऑप्टिकल पाथ इन अ मीडियम आला आणि त्याच्यामध्ये जेवढं डिस्टन्स ट्रॅव्हल केले या सगळ्या गोष्टी आल्या आणि त्या गोष्टी आपल्याला इथं बघायच्या आहेत. डेल्टा फाय डॅश इज इक्वल टू डेल्टा फाय डॅश इज अ फेज डिफरन्स इज इक्वल टू के डॅश इंटू डेल्टा एक्स इज इक्वल टू ओमेगा एन डेल्टा एक्स अपॉन सी is equal to omega delta x dash upon c, where delta x dash is equal to n into delta x, optical path traveled by a wave. Next, optical path in a medium, time is equal to distance upon speed, and this equation is we studied in the last few minutes. The distance d traveled in a medium of refractive index n introduces a path difference, and this is here AD is equal to AD into n minus 1 is a path difference. If a thin transparent plate of thickness t and refractive index n is introduces the path S1p of the interfering wave, it is observed that the entire fringe pattern is shifted upward through distance given by capital D upon D into n minus 1 into t, where d is the distance between source and the screen, small d is the distance between two slits, and t is time, n is refractive index. All these terms are known. The introduction of plate has no effect on the fringe width. Next, diffraction of light. The bending of light near the edges of an obstacle or slit and spreading into the region of geometrical shadow is known as diffraction of light. सगळ्यांना स्क्रीनवर एक हे दिसतोय, छोटासा व्हिडिओ दिसतोय की डोअर ओपन होतोय आणि डोअर ओपन होतोय, डोअरच्या आतमध्ये अंधार आहे, रूममध्ये अंधार आहे पण बाहेर उजेड आहे. मग तो जो सगळा लाईट आहे तो डोअर ओपन केल्यानंतर डोअर जेवढा ओपन होईल तेवढ्याच प्रमाणात तो आत आलाय, त्यालाच म्हणतात बेंडिंग ऑफ लाईट, अँड दिस इज अ एक्झाम्पल ऑफ डिफ्रॅक्शन ऑफ लाईट. Types of diffraction. There are two types of diffraction. First is Fraunhofer diffraction and other is Fresnel diffraction. What is the difference between these two diffractions? In Fraunhofer diffraction, the source of light and screen are kept at infinite distance from the diffracting system. In Fresnel's diffraction, the source of light and screen kept at finite distance from the diffracting system. Here are the two diagrams. We see here Fraunhofer diffraction and Fresnel diffraction. Fraunhofer diffraction. This occurs when all the rays passing through a narrow slit are approximately parallel to one another. This can be achieved either by placing the light source far from the opening used to create the diffraction as shown in the figure below. The important points for Fraunhofer diffraction are the screen the screen and the source are at an infinite distance from each other. The incident wavefront are horizontal. C. The plane or horizontal wavefront are connected using a convex lens to produce a diffraction pattern. And D. Plane diffracting waves are conserved using a convex lens to produce a diffraction pattern. Fraunhofer diffraction मध्ये convex lens is important. Fresnel diffraction. In Fresnel diffraction, the source of light and the screen on which the pattern of diffraction is obtained are effectively at finite distance from the diffracting system. The important points for Fresnel diffraction are the screen and the source are near to each other. The shape of incident wave fronts are spherical or cylindrical. The objects left by the wavefront are spherical. A convex lens is not needed to converse the spherical wavefronts. Convex lens in Fresnel diffraction, convex lens is not needed. Experimental setup for Fraunhofer diffraction. Here is the diagram which is a setup for Fraunhofer diffraction, which is experimental setup of Fraunhofer diffraction. S is S denoted source, Y and Y dash are the wavefronts, M, N is a lens. Here focal length is nearly equal to capital D. P0 and P are the maxima and minima. The figure shows a monochromatic source of light S at the focus of a converging lens. Ignoring aberrations, the emerging beam will consist of plane parallel rays resulting in plane wavefronts. These are incident on the diffracting element such as a slit, a circular aperture, a double slit, a grating, etc. Emerging beam is incident on another converging lens that focuses the beam on a screen. In the case of circular aperture, S is a point source and lenses are biconvex. For linear elements like slits, grating, etc., the source is linear and the lenses are cylindrical in shape so that the focused image is also linear. In either case, a plane wavefront, if the source is at infinity, approaches and leaves the diffracting element. This is as per requirements of Fraunhofer diffraction, and all these things are required in experimental setup for Fraunhofer diffraction. Fraunhofer diffraction at a single slit, and here is the diagram for Fraunhofer diffraction at a single slit. In this single slit Fraunhofer diffraction, one slit considered AB is a slit and A is a slit width. P0 and P are the maxima and minima, and theta is the angle made by the P0 and P. From triangle ABC, see the figure, from triangle ABC, sine theta is equal to BC by AB is equal to BC by AB. BC is equal to sine AB sine theta is equal to A sine theta is equal to A sine theta. Position of secondary minimum which is A sine theta. A position path difference is integral multiple of lambda, then secondary minima is obtained. A sine theta is equal to n lambda, where n is equal to 1 plus or minus 1 plus or minus 2 plus or minus 3 and so on. Position of the secondary maxima, path difference is odd multiple which is lambda by 2, then secondary maxima is obtained. A sine theta is equal to 2n plus 1 lambda by 2, where n is equal to plus or minus 1 plus or minus 2 plus or minus 3 and so on. Width of a central maximum is equal to WC is equal to 2 into lambda d divided by A. These are the things for maxima and minima and central width. Comparison of Young's double slit interference pattern and single slit. Here is the Young's double slit interference pattern and single slit diffraction pattern. Interference and diffraction are related terms. If interference happened, diffraction is must happens. Fringe width W is equal to in interference pattern lambda d upon d, W in diffraction pattern lambda d upon A, except for the central bright fringe. For nth bright fringe, phase difference delta between extreme rays n is equal to n into 2 pi, and for diffraction n plus 1 half into 2 pi. Angular position theta n into a lambda by d, and for diffraction n plus 1 half lambda by d. Path difference delta x between extreme rays in interference n lambda and diffraction n plus 1 half into lambda. Distance from the central bright spot denoted by y, and for interference this is n into lambda d upon d is equal to nw, and for diffraction n plus 1 half lambda d upon A, which is also equal to nw. Phase for nth dark fringe, phase difference delta between extreme rays n minus 1 half into 2 pi, and for diffraction n into 2 pi. Angular position theta for interference it is n minus 1 half into lambda by d, and for diffraction n into lambda by d. Path difference delta x between extreme rays n minus 1 half into lambda, and for diffraction pattern n lambda. Distance from the central bright spot y n minus 1 half into lambda d upon d is equal to nw, and for diffraction it is same, n into lambda d upon a is equal to nw. W is width of a central fringe. Here some images, which images? Image A shows Young's double slit interference, image B shows single slit diffraction, and image C shows double slit diffraction. Next point, resolving power. What is meant by resolving power? Ability to distinguish two physically separated objects as two distinct objects is known as resolving power of an optical instrument. आता इथं काहीतरी इमेज तुम्हाला दिसते, अँड व्हॉट इज मीन बाय रिझॉल्विंग पॉवर? तर इमेज ज्या वेळेला आपल्याला दिसतात तर काय आहेत की एकमेकांमध्ये इन्सर्ट झालेले इमेज आपल्याला दिसतात, की इथं जर तुम्ही वेव्ह स्क्रीनवर बघितल्या अनरिझॉल्वच्या, तर ह्या सगळ्या वेव्ज एकमेकांमध्ये काय झाल्यात, मिक्स झालेल्या आहेत. मग आता ह्याच्यामध्ये हे जी ॲबिलिटी आहे की त्या सेपरेट डिफाईन करायची, त्याला म्हणतात रिझॉल्विंग पॉवर. In figure A, unresolved. Two objects are said to be unresolved if the separation between the central maximum of the two objects is less than the distance between the central maximum and first minimum of any two objects. In figure B is just resolved. It means if the central maximum of one falls on the first minimum, it called just resolved images. And in figure C is a well resolved. We can define two separate images if the separation between central maximum of two objects is greater than the distance between the central maximum and first minimum of any two objects. And this is Rayleigh's criteria for resolution of objects. Two linear objects. As per Rayleigh's criteria, angular separation position of the first principal minimum of d theta is equal to lambda by a. Limit of resolution of that instrument, limit of resolution is equal to d theta is equal to lambda by a. Then minimum separation between two linear objects are just resolved at distance d from the instrument is y is equal to capital D into d theta is equal to d lambda upon a. Pair of point object. A schematic diagram show formation airy disk and rings. And figure B shows the real airy disk obtained by using a laser. एक सर्क्युलर अपर्चर आहे, त्याच्या सर्क्युलर अपर्चरमधून सोर्समधून लाईट हे जाते, पास होते, आणि त्या पासमधून ज्या डिस्क तयार होतात त्यामध्ये एक सेंट्रल डार्क आहे, आणि ज्या काही ब्राईट फ्रिंजेस आहेत त्याला काय म्हणतात, आयरीज disk or rings. The diffraction pattern of such objects consists of a central bright disk around disk by surrounded by an centric rings. Resolving power of a microscope. Here the figure shows resolution of object by a microscope. Sorry, and figure B shows enlarged view of region around the O and O dash. Microscope with a pair of non-luminous objects, dark objects. Non-luminous म्हणजे कोणताही प्रकाश सोडत नाहीत. With a pair of non-luminous objects, minimum separation for resolved images A is equal to lambda upon 2n sin alpha is equal to lambda into to n into a. N into a is a numerical operator. Resolving power R is equal to 1 upon a is equal to 2 into na upon a. Second, microscope with self-luminous point object. Self-luminous means त्याच्यामध्ये काहीतरी स्वतःचा थोडासा लाईट असेल असं. मग just resolution 2a sin theta is equal to 1.22 lambda. This is the formula for just resolution. A is equal to 1.22 lambda upon 2 sin theta, sin alpha. A is equal to 1.22 lambda 2n sin alpha is equal to 0.61 lambda upon n sin alpha is equal to 0.61 lambda into na. Therefore, resolving power, which is denoted by R, is equal to 1 upon a is equal to n into a upon 0.61 lambda. Resolving power of a telescope. Resolution of a telescope. या इमेजमध्ये तुम्हाला रिझोल्युशन ऑफ टेलिस्कोप दिसतच आहे. रिझोल्युशन मीन्स सेपरेशन ऑफ द इमेजेस, म्हणजे जे काय इमेज एकमेकांमध्ये मिक्स होऊन जी आपल्याला ब्लर इमेज मिळते, मग त्या दोन्ही इमेज व्यवस्थित जर दोन पॅटर्न जर एकत्र झाले तर त्याच्यामध्ये जे ब्लरनेस येतो तो आपण सेपरेट करू शकतो बाय युझिंग रिझोल्युशन. रिझोल्युशन ऑफ टेलिस्कोप. D is the aperture of the telescope, diameter AB of its object. Therefore, BI dash minus AI dash is equal to D into theta is equal to 1.22 lambda. Therefore, theta is equal to 1.22 lambda upon D and R is equal to 1 upon theta is equal to D upon 1 upon 22 lambda. Radio telescope. रेडिओ टेलिस्कोप. GMRT रेडिओ टेलिस्कोप ह्या फिगरमध्ये तुम्हाला दिसतच आहे. GMRT लोकेटेड ॲट नारायणगाव नियर पुणे जे रेडिओ टेलिस्कोप आहेत आणि हे रेडिओ टेलिस्कोप काय असेल ते रेंज काय असेल ती कॅप्चर करून आपल्याला सिग्नल देतात. द हायेस्ट अँग्युलर रिझोल्युशन अचिवेबल रेंज इज फ्रॉम अबाउट 60 अरसेक. अरसेक इज 3600th part of a degrees. Lowest frequency of 50 megahertz to about 2 arcsecs at 1.4 gigahertz. And this is a radio telescope and this is the ability of a radio telescope. आता रेडिओ टेलिस्कोप काय आहे तर आपल्याला जवळ बघायचं असेल तर पुण्याजवळ तुम्हाला बघायला मिळेल. अँड हिअर वी एंडिंग दिस चॅप्टर वेव ऑप्टिक्स. थँक यू फॉर वॉचिंग. थँक यू.